Okay, so you should have this note template in your, again, this is posted in the Google Classroom. So this is about vectors in 2 dimensions. Okay, so vectors generally can be represented by arrows. So usually we try to represent them with arrows, wherein the length of the arrow represent the magnitude, and the direction where the arrow points would be the direction. And so if your vector is lying in a xy coordinate system, so let's say for example I have is y x, and then the vector is somewhere here. Okay, so if this is my vector a, so represented by a there, this particular vector is made up of 2 components. One is along y, so just a projection of your vector towards the x-axis. This is the x component of that vector a, as well as if you're going to project the tip of your vector towards that the y-axis, you're creating yourself the y component of your vector a. Okay, so when adding vectors, individual components are combined using, so if you can see here, breaking down your vector into its components, you're actually just making up a right-angled triangle. And based on what you've learned in trig, if you have a right-angled triangle, Pythagorean theorem can be applied. Okay, so again, just a review of your Pythagorean theorem. The longest side is just equivalent to the square of the sum of each side. So that's a Pythagorean theorem. So you have your right angled triangle here. C is the longest side. A and B are your 2 different sides. Okay. So specifically, let's take this example here. You have vector components, as I've mentioned. A particular vector can be broken down to its components, the x and the y. So since you are just creating a right-angled triangle, we can use the trig ratios. So specifically just sine and cosine. So if you can remember your trig ratios, we have 3, we have sine, cosine, and tangent. Okay, so sine, cosine, and tangent. And by definition, if you can remember, sine is defined. Sine of a particular angle is just opposite over the hypotenuse. Cosine of a particular angle is just the ratio of the adjacent side over the hypotenuse. And the tangent of a particular angle is just the ratio of the opposite side all over the adjacent side. So, or widely known as SOHCAHTOA. Okay, so just use the acronym SOHCAHTOA to remember the different ratio. So if you can remember here, or if you can see here, this is sine of an angle is just equivalent to the ratio of the opposite side over the hypotenuse. Hypotenuse is the longest side of your right triangle. So if you can remember that. So in this particular case, we have a particular vector represented by 20 meters per second, and its direction is 30 degrees north of east. So we can actually call this one as our vector A. So that would just be 20 meters per second. So that's the length of this line here. And its direction is given by 30 degrees. 30 degrees north of east. So again, I can write that one, that particular vector is just 20 meters per second. That's the magnitude. The direction is 30 degrees north of east. Okay. If you're wondering, how do I know that it's north of east? Well, if we're gonna use the direction here, going up is north, going down is south, this is west, and this is east here. And if you can see, the reference of your angle 30 degrees is actually from east. So by this notation, although if you're using other books also in physics, depending on your the book that you're using, sometimes they try to interchange this too. But with this notation here, if you're gonna use north of east, or the two directional, like this one here, the last direction is your reference of the angle measurement. So try to take note of that. This is the reference. So reference of angle measurement. Okay. So if I measured from east, the last direction should be east. We know that this is between north and east. However, what would be our basis for north of east? Well, that is where you started your measurement of 30 degrees. Okay. So if you use the other side, this particular direction could be written as what is 90 minus 30, that's 60 degrees. So it can also be 60 degrees east of north. So that is just the same thing. But in this particular case, the angle measurement is 30 degrees and it is measured from the east. So therefore, you're gonna give the direction as north of east. So again, the last direction involves the reference of your angle measurement, or that is where you started measuring that particular angle. So 30 degrees is measured from 30 degrees. So now, if you want to get the x and the y component of your vector A, you just make use of your trig ratios. So again, if you can see here, this is a right angled triangle. So therefore, you can assign the different sides. Remember that the longest side will always be the hypotenuse. Okay? But the opposite side and the adjacent side depends on your location of the angle. So if you can see here, I'm talking about 30 degrees. So when we say opposite, the side that is opposite to your angle. So this one would be the opposite of your angle 30 degrees. So therefore, this particular line here is the opposite. And adjacent side, meaning of that one is just beside the angle. Uh, of course, we can no longer assign this particular side here as the adjacent side because that is the hypotenuse. That would be, again, by definition, that is always the longest side of your right angled triangle. So therefore, the adjacent side is this one here, the base of your triangle. So this is your adjacent. Okay. So again, if you can see here, it's based on the angle. The definition of your opposite adjacent, especially for opposite and adjacent sides, it is dependent on the location of the angle. Again, the one that is fixed here in your right angled triangle is just the hypotenuse, because the longest side is defined as the hypotenuse. And to determine the opposite side and your adjacent side, always think of the location of your angle. And from the location of your angle, you can identify which is the opposite side and the adjacent side. Okay, now we already identified the different sides here. So if we want to solve the y component, so the y component is just given by this one here. This is just your y component. So this particular side is the y component of this vector A. So I call that one as AY. Okay. So how would I solve for AY? 20 meters per second is the magnitude or the length of this side here, the longest side or the hypotenuse. And then I'm given the angle 30 degrees. And then AY is the opposite side. So if I want to solve for the y component, solve for AY, okay, the y component, I'm just going to look at my triangle again. Well, I've given the longest side, hypotenuse, the angle, and the unknown is the opposite side. So looking at my SOHCAHTOA here, the one that will enable me to solve the particular opposite side would be the sine function, because everything is given except for the opposite side. So therefore, that would be sine of 30 degrees is equal to the opposite side is AY all over the hypotenuse is 20 meters per second. Or if you're going to solve for AY is just 20 meters per second multiplied by sine 30 degrees. So that would give you an answer of 10 meters per second. So that is the y component of my vector A. And now if you want to solve for the x component, so the x component is just this one here. And that is represented by the adjacent side of this right triangle that I made. So if you want to solve for ax, or the x component of your vector A, so you look at your triangle. The x component is the adjacent side. I've given the hypotenuse. So which of the three functions, trig functions that you can solve for the adjacent side? Well, that should be cosine. Again, cosine of the angle. Cosine of an angle, which is in this case 30 degrees, is equal to the adjacent side, which is AX, and then the hypotenuse is 20 meters per second. Or you can have AX is equal to 20 meters per second multiplied by cosine of 30 degrees. So if you're going to solve for that, AY, not AY, but AX is equal to 17 meters per second. So that is the X component of my velocity. Oops. Okay, any question with this one here? Did you somehow remember your trig, right? So you're actually allowed to write this one in your formula sheet, or if you have one, if you need to. Again, I will give you this trig ratio here, but just try to remember the different placement of the different sides. Again, it is dependent on the location of your angle. So it would depend on that. Okay. So maybe let's try to do example number 1. A girl runs at 30 degrees north of west with a velocity of 2.5 meters per second. What are the x and the y components of her velocity? So for this type of questions, it's always good to start it with a diagram, especially if you can see here, it's dependent on the location of your angle when you try to employ the different trig ratios. So now, the first thing you need to do is the location of this particular vector. It's north of west, 30 degrees north of west. Okay, remember that to identify where should I start measuring my 30 degrees, I'm gonna look at the last direction. So that means that this 30 degrees is measured from west. Okay, so if I'm gonna draw my vector, I know that it is in the second quadrant. So this particular vector should be in the second quadrant. Okay, so with a magnitude of 2.5 meters per second. But now to identify its direction, this is very crucial because if you somehow misplace the location of the angle, that could again make a lot of difference. You will get a wrong answer. Okay, so north of west. So that means that this 30 degrees is measured from west. And if you're gonna place a small crosshair, so this is the case, you always, the tail of your vector, that is always be the basis of your angle measurement for the direction. Okay, so it is from the tail. You will not measure the direction from the tip. It should be coming from the tail. So that's 30 degrees. That's coming from, measured from west. So west is this side here. This is west. So that 30 degrees that is located somewhere here. This is my 30 degrees. Okay. Remember that if you interchange that one, if you place the 30 degrees here, you'll get a different answer. Okay. So that's the first thing that you need to do. Try to properly locate that particular direction or that particular angle. So that's 30 degrees there. Now we want to get the x and the y. So the x component and the y component. So in this particular case, the x component is just the, again, it's just the same thing as the tip of the vector towards the x-axis. So this would be your x component. I'm just going to call this one as Vx. And the y component is just the component that connects Vx towards the tip. Okay, so this is my Vy. So now to uh, to identify the different sides again for the SOHCAHTOA thing, the placement of those sides are specific. Okay, and it's always good to start with identifying with the sides. So in this right angle triangle here, if you can see it, if you're gonna make your Vx and Vx and Vy are always perpendicular to each other. That means that they make 90 degrees. So if you're gonna make your Vx and Vy, you will always create a right angled triangle. And again, if you have a right angled triangle, you can use Pythagorean theorem and the trig ratios. And just identify the different sides. Again, the longest side will always be the hypotenuse. In this case, Vx becomes your adjacent side, and the opposite side is your Vy. Okay? So now, if you want to solve for Vx, so Vx is just equivalent to 2.5 multiplied by cosine of 30 degrees. And that gives you 2.2 meters per second. And then for Vy, it is just 2.5 multiplied by sine of 30 degrees. And the answer is 1.3 meters per second. Okay. So this would be the x and the y components of your velocity. So this is the x component, and the other one is the y component. Okay. So any questions with this example here?
Yes, I have a question.
Yes. Okay.
It's like since it's west, does that change anything with like the
Sine.
the
The
negative?
sine.
Yeah.
Yeah, that's correct. So yeah, I forgot that one. The x and the y component, that is also important, by the way. In this case, since this is west, Vx becomes negative. Forgot that one. And your Vy is just
It's still
positive.
positive. Yeah. Yeah.
Yes,
Okay.
yes. Okay, great. Thank you for
Okay.
that.
Thanks.
Yeah. So yes, that is also important. The x and the y component is essentially because we're still using the Cartesian coordinate system here. So the Cartesian coordinate system that we're using is that first quadrant both are positive, second quadrant negative x, positive y. By the way, you need to remember that one also in getting for the x and the y components, because again, essentially these are vectors. Okay, because later on it will be shown that this particular vector of 2.5 meters per second north of west can be represented by 2.2 meters per second west plus 1.3 meters per second north. So it gives you the same, the sum of Vx and Vy is equivalent to this 2.5 meters per second here. Okay. Remember that these are vectors. Again, vectors. Uh, you cannot add, let's say, 2.2 plus 1.3, like Like for example, in this case here, if you have 2.2 meters per second west plus, if you're gonna add it with 1.3 meters per second north, it doesn't give you 3.3. Okay, this is not equal to 3.3 meters per second something. The reason for that is of the direction. The direction are, well, one is in the x component, the other one is in the y component. So if they are of different components, you cannot add them algebraically. So it's not something like as simple as just adding uh, the magnitude. So you have to take into account both the magnitude and the direction. And I think later on we'll be discussing that one also. Okay, let's take example number 2 here. A car travels with a velocity of 55 kilometers per hour at 25 degrees south of east. What are the south and east component of this velocity? So in this particular case here, specifically, we're just being asked the south component and the east components. So, or this is the same thing as your y, and this is your x components. Okay, so you could be asked this way. So it only means the same thing. You're getting the x and the y components of your velocity. And again, to start with, you try to locate this particular vector. Where does this particular vector will lie? Well, it's southeast, so that would be in the fourth quadrant. So if I'm gonna draw that one, so your drawing doesn't necessarily have to be that accurate, meaning that the angle of 25 degrees uh, would be from your drawing. Sometimes it's helpful to just place your vector in a proper location, and that's good enough. So southeast, that would be in the fourth quadrant. And now for the angle of 25 degrees, again, it is south of east. So that means that my angle 25 degrees should be measured from east. So that should be the 25 degrees is here, okay? So I would suggest that you should always start with that, the proper location of your angle measurement. Because if you somehow misplace the location of the angle, remember that when you get the the ratio of the trig ratio is also dependent on the location of that angle. So somehow if you miss the location, you'll get a different answer. Actually, they will interchange. That's the effect of that one if you try to interchange the two. So now, the magnitude of this one is 55 kilometers per hour. So my x component is this one here. So this is my Vx. And then Vy is uh, going down. Remember that the arrow of my Vy is going down. You cannot do it going up because it is the projection from your, again, it's coming from the point of your resultant vector towards the y-axis. Then, okay, that's why it's pointing downward. It's not pointing upward, okay? It should be pointing that way. Now, I will identify the different sides. Again, if you can see here, Vy and Vx are always perpendicular to each other, meaning they're 90 degrees apart. So I will identify my different sides. Hypotenuse is always the longest side. And in this case, Vx would be my adjacent and Vy is my opposite side, okay? So now, if I'm gonna solve for Vx, so Vx is just 55 multiplied by cosine of 25 degrees. Oops. So Vx is just 50 kilometers per hour. Well, negative, that's positive. Or if there's a question that specifically asks for its direction, you will actually say 50 kilometers per hour east. Or in this particular case, well, automatically, whatever is your x component would be directed east. But just in a case wherein you'll be asked to solve for the x component, its direction, well, it should be directed east. Or if we're gonna use this one in a computation, instead of using the east, we use the symbol plus. Again, later on, if we're gonna add vectors, this particular sign of your Vx and Vy will play an important role. And then for Vy, it's just 55 multiplied by sine of 25 degrees. So Vy is equal to 23 kilometers per hour. In this case, it's downward, so it's negative. Or if we're going to use the direction, that's 23 kilometers per hour south. Okay. Again, we use the signs when we try to use this one in a calculation. Okay, so this will lead up to the next topic wherein if we have one or more vectors to be added. So to add vectors, there are different methods that you can use, but this should be the general method. That means that the steps here can be employed even though you are adding 100 vectors. You just
Mr.
have
Villarin, before we continue, I have a question.
yes.
For example 2, so even though the triangle is in quadrant 4 where x and y would be both negative, since it's in east direction, it's still positive for x?
In the fourth quadrant, I believe in the fourth quadrant, x is positive, right? Fourth quadrant.
Oh, sorry. No, yeah.
So,
Sorry.
yeah, it's all good. Yeah. So, yeah, we just, yeah. So if we use the Cartesian coordinate system, if this is positive y, negative y, this is negative x, positive x. We just use this one that this is both positive here. This one is negative, positive. Both are negatives here, and this is positive.
Yeah, I switched
Negative.
quadrant 3 and 4 by accident.
Yeah, it's all good. Yeah, that's why also here, relatively important to actually place your pointer in a proper way, because sometimes if you're gonna miss this one out, like if you try to do the other direction, well, that becomes second quadrant, and that messes up your solution because that is a different direction. Okay, so for these steps here, this is the general, actually can be employed even though you have more than even 100 vectors. You're gonna do it this way, you still get the final answer. So um, we try to draw a diagram. So it doesn't have to be perfect, but reasonable. So the meaning of that one is, as long as it is in the proper direction or in the proper quadrant, you're okay. So even though this is not necessarily perfectly 25 degrees here in my drawing, but at least I know that it should be in this quadrant here, the fourth quadrant. And yeah, even though if you're, let's say, if this is 10 degrees, you don't have to draw it like very close to that. You can actually still draw it this way, like even though it's bigger than 10 degrees. But again, important thing there is that it should be located in the proper quadrant. And you use so to resolve each, so sine, cosine, or tangent, each vector into x and y components. Okay, and then you get the total of each, and then use Pythagorean theorem to find the resultant. When you say resultant is just the sum of all vectors. So resultant is another term that we use if we're gonna take the sum. Okay. So just an example, essentially, if you're gonna draw, like you have vector this, and then added with a vector going north, and then another vector going in this direction, okay, and a vector going south, for example, okay. So how would you draw your resultant here? So this is an important thing because most students will miss this one out. Okay, so this is your first vector here. This is your vector. Uh, say this is your A, B, C. So A, B, C, and then D. Okay, so if I gonna add everything, this is how I add in using diagrams. So if you can see, I just placed the second vector to be added at the tip of my first vector, then so on and so forth. So now, this is an important thing to draw the resultant vector. To draw the resultant vector is drawn from, so it's from the tail of the first vector that you add, towards the tip of the last vector added. So therefore, the direction is going to there, okay? From the tail of the first vector towards the tip of the last vector added. So this is your resultant vector, okay? This block line here. So it's not the other way around. Don't try to place it from D, from the tip of D towards the tail of A. So the resultant vector is drawn from the tail of the first vector towards the tip of the last vector added. That's your resultant vector. And if you can see here, this is just the sum of all the x and the y components of all of the vectors here. So it can be represented by just, this is your Rx, if you can see. This would be your Rx, and this is your Ry. And that is just the sum of all the x component of A, B, C, and D. Although B and D don't have any x components, but if you can see, if you're gonna draw your A here, you have, this is my AX, right? And then if you can see here, this is just my CX. And for my Y, is it not that everything that is going up here for my AY, that is just being countered by this dy that is downward, and this by here is just being countered by whatever is my cy, I mean. So essentially that just becomes this triangle here for my r downward. But we will be doing, this is just graphically or showing by diagrams, that everything can just be, again, just the sum of the x and the y components. And if you have noticed, we try to indicate the signs, because if I gonna add my ax and uh, let's say my by here and cy, that is 0, because by is going up, this cy here is going down, and their length are the same. So therefore, when I try to add algebraically, that gives me 0. And this ax here is upward, but this dy is going downward. So if I'm gonna add that 2, somehow portion of your dy is being taken off by the positive ax or ay that I have. Okay, so again, this is just a review of the direction. So angle isn't enough. It should be indicated relative to what? So the reference angle should be north, east, southwest. North is up, east is right, south is down, west is left. So if you can see east of north, so starting from north. So this is what I mentioned earlier. So if it is written this way, that means that 30 degrees is measured from 30 degrees. So towards east. And don't worry, I will not be using a different notation. I will not be using a different notation in the direction. So let's just stick with this one here. So if it is given this way, just think of whatever is the second direction. That would be the reference, or that would be where the angle measurement is coming from. Okay, so any question with this one here? Especially for the direction part. Remember, that is kind of specific. You have to be aware where should you place that particular angle measurement. So again, I will not be using different notations, because you also have other notations, maybe some other problems. And even for, I think for pre-calc book that you have, they're not using this notation here. They're using a different notation also. But in our case, in Physics 11 so far, and I believe that this is also the notation being used by Mr. Su. So just familiarize this particular notation for the direction. Okay. And I believe also that your book uses this particular notation. I'm not saying that this is the only notation that you'll be encountering. Other books uses a different notation. But in our case, just stick to this one here. Okay, so another way of, especially if you only have two vectors, you can actually use the sine law and cosine law. So uh, although I would suggest this particular method here to add vectors, because anyway, this is the more general way of adding vectors, this one here. Because if you're going to use sine and cosine law, this is only applicable for two vectors. Okay? If you're adding two vectors, well, this is okay, sine law and cosine law. But if you have three vectors, that means that somehow you need to resolve first the two vectors into one vector, and then before you can employ sine law and cosine law. Okay, so it's also your option, but this is only limited for two vectors added. Okay, so directly you can use this one for two vectors added. Okay. However, for three or more, well, you have to somehow resolve it first into two vectors before you can use this sine law and cosine law. So I would rather focus on this part here, because even though you have 1000 vectors, you can still solve it. Maybe it is much longer, but still you'll come up with the correct answer. And it's always good to just familiarize. And I believe that have you done sine law and cosine law already? I think not yet, right?
No, we haven't done it yet.
So yeah, might as well just focus on this one here, because in resolving the vectors you just use trig ratio and essentially Pythagorean theorem, which is, I believe you've done it in grade starting grade 8. So somehow you have it's more familiar with you than having the sine law and cosine law. But again, this is also in your arsenal, or I mean one of the options that you can do. Okay, so we move on to vector subtraction. Okay, to subtract, because anyway in our case we'll just do addition and subtraction. We will not do any multiplication. uh, yes, so just vector addition and subtraction. So just try to remember that when you're subtracting two vectors, that is just the same thing as this one here. If you can remember, maybe when you talk about integers, when you talk about integers in your grade, maybe grade 7, one way of looking at subtraction is adding the opposite. Okay, uh, subtraction symbol is the same thing as you're adding the opposite. That's why you can actually express that one as plus the negative of b. So if you are subtracting vectors, just try to remember that it is just the same thing as adding the opposite of that vector. Okay, so let's take for example here, this is vector a added with vector b. Okay, so the resultant vector, or again, resultant vector is just the sum. So essentially that is just the same thing as a plus b, which is given by this line here. Okay, so therefore a plus b is given by just this single line here. Okay, so now if you are subtracting a minus b, again, that is just the same thing as vector A. Again, if I gonna say that in words, vector A added with the opposite of vector B. Okay, so what is the opposite of vector V? Is it not that when we talk about integers, that is just the negative, the negative or the opposite direction of that, then just the negative of that particular vector. So that's why we have a negative sign here. Okay, opposite of vector V. So a negative vector, therefore, is just a vector whose magnitude is the same but opposite with the original vector. So vector B, remember that vector B is represented by going to the right. So this is your vector B. So if I'm going to represent a negative vector B, it is just a vector of the same length of that vector, the same vector B, the same magnitude, but the arrow should be placed on the opposite side. So that is why its length would be the same, but the direction is 180 degrees apart from the original vector B. So therefore, in this particular case, this A minus B is just equivalent to A plus the negative of B. Okay? So again, if you can see, nothing changes with my A. A is the same thing. Okay? Still going up. But now, instead of going to the right, I am moving to the left because my vector B, the direction is west. But what is the opposite of west? No, it's east. The opposite of east is west. So therefore, the direction of my negative B is towards west. And same thing here, you have B minus A. But if I'm going to write it out, that is just the same thing as B plus the negative of A. So is it not that when we try to write our vector, vector B is towards right or east, okay, but plus the negative of A. A is going north. So therefore, the negative of A is going south. So that is downward. So that's the negative of A. Because positive of A is going upward. This is your positive A. So the same length, again, a negative vector is just defined that way. It's just the magnitude is the same. However, the direction is completely in the opposite direction or 180 degrees apart. Okay. So any question with subtraction here, because later on, although not so much with physics 11, but this is much more applicable when you are doing in physics 12, like change in momentum, something, because change in momentum is a vector quantity. So therefore, change in momentum is P2 minus P1. However, that is just the same thing as P2 plus the negative of P1. So you're going to do it this way. You're adding the opposite. Again, it's just becomes simpler if you're just adding them, because we set up previously on how to add, essentially how to add vectors. We just have to place them from head, then this one here. So we started with the first vector, added with the second vector. We just tried to place it at the end of our first vector, and then draw our next vector, and so on and so forth. So make sure that if you see a subtraction symbol in your operation, if you're subtracting, that is just the same thing as adding the opposite. So another example of opposite vector is that if your vector, certain vector d, for example, if this is my vector d, the negative of that vector is just a vector with the same magnitude but opposite in direction. Okay? Or let's say, for example, if I'm gonna ask you, let's say I'm given vector f as 10.0 meters, 30 degrees north of east. So what do you think is negative f? Okay, so negative of f is a vector with the same magnitude of this. So same magnitude, so that means that 10 meters is the same, but it should be in the opposite direction. So if this is 30 degrees north of east, this should be in the south of west. Opposite also. So if you're gonna draw this one, north of east is uh, this particular vector is should be somewhere here. So that is my f. This is 30 degrees. And if I'm gonna draw my negative vector of that, so that means that that is just in the south of west. So if you can see, that is just somewhere here. This is my negative f. This is the 30 degrees here, south of west. And if you can see, that is just a straight line, but they are 180 degrees apart each other. Okay, any question with this one here? Negative vectors. Again, don't be tempted. Let's say, for example, in this case here, I specifically given the direction 30 degrees north of east. If I have a negative vector of f, just don't place negative 10 here, okay? Because remember that it is in between south and west. That's okay if you're just talking about north, 10 meters north. Obviously, the negative vector of that one is 10 meters south. But in this particular case, remember, the direction is you now have components of your two vectors here, vector f and the negative vector f. So how would you change the direction? If you can see, that is just opposite. North, the opposite of north is south. The opposite of east is west. And yeah, you get the negative vector there. Okay, any questions with that? If there's none, before we proceed to example number 3, uh, let's